Good morning. Let us continue our discussion of the subject fundamentals of data science. This is unit 1 and we have already covered definitions, hype, datafication, data science profile, meta definition, data scientist. Today we will be discussing on statistical inference, populations and samples of big data. Big data can mean big assumptions, and for this we are using the prescribed textbook by O'Reilly called as Doing Data Science by the authors Rachel Shutt and Kathy O'Neill. These were the topics which we had covered previously. So today we'll be discussing this statistical inference. We know that exploratory data analysis is a major aspect in data science. And when we speak about exploratory data analysis, what usually comes to mind is calculating means, medians, minimum, maximum, quartiles, finding outliers, drawing plots, graphs, summary statistics, which we just mentioned. So what exploratory data analysis indicates is it's a method of systematically going through the data, plotting distribution of all variables, using box plots and various other plots, plotting the time series data, transforming variables, finding relationship between variables using scatter plot matrices, and generating summary statistics. Now, why EDA? Why exploratory data analysis? Basic thing is I need to gain intuition about the data. I need to make comparisons between the distributions. For sanity checking, making sure that the data is on the scale you expect, in the format you thought it should be. To find out where data is missing or if there are outliers, and to summarize the data. EDA also helps in debugging the logging process. You may find patterns wherein through those patterns you may identify what is wrong in the logging process and fix it. Now coming to the topic statistical inference. So as we perform various activities like commuting for work, blood samples, going shopping, sending emails, browsing the internet, stock market, eating, talking. So all these activities will be producing data. So these are the processes in our lives, and these processes in our lives are generating data. What exactly is data? Data represent the trace of the real world processes, and which traces we gather, that is decided by sampling methods. Now from this what we understand, what is a processor, what is a data, and what is data collection. And from this we also understand that there is lot of randomness and uncertainty. So randomness and uncertainty is there in the process as well as in the data collection. Now once I do the data capture, I need to simplify that data, I need to comprehend that data, and that is done with the help of mathematical models or data functions, and they are known as statistical estimators. Now what is happening here is the real world life is being captured in the form of data, and that data is being again analyzed and being sent back to the world. This is called as statistical inference. So, coming to the definition of statistical inference, it is the discipline that concerns with the development of procedures, methods, theorems that allow us to extract meaning and information from data that has been generated by stochastic processes. So, ultimately, this last paragraph is deriving the meaning of statistical inference. So, what is it deriving? It is saying that data we have collected from our real world life, there is randomness in that. Okay, so the statistical inference involves procedures, methods, theorems which will be used to extract meaning and information from this collected data. Now, coming to the two words populations and samples, we know, say for example, population of India, that is an example of population, but here what will be the sample? Maybe all men in India, or all women in India, or children in India, that can be a sample. Population example can be total number of tweets, population example can be total number of photographs. So, the population, suppose population of India is X, number of tweets are Y, number of photographs are Z. So, these will be the observations. Okay. So, when I say N, I am speaking about the observations in that population. So, when I am speaking about emails, I am speaking about the observation, N indicate the observations in the emails. Now, I will take a small n here to represent a sample. Let us say total emails is capital N, then small n will be a sample which can be a 1/10 of the emails sent today, or 1/10 of the employees we capture, and their emails will be compiling. So, whenever we are sampling, there is a scope or chance for bias and distortion. Now, the same word population and sample in the context of big data. So, all the major companies like Google or anywhere, statisticians as well as data scientists are sampling a lot. That depends totally, like whether you need a sample or not. Suppose you are doing some analysis or you want to draw some inference, then you may need a sample. But suppose you want to render a UI, or you want to serve some purpose, then in that case you need the entire data, entire population. Now, whenever we are taking a sample, or whenever we are taking a population of, from the data corpus, any inference drawn should not be treated as conclusions, because there is a problem. What that problem is highlighted by this Kate Crawford, who in her article Hidden Biases of Big Data. Suppose there was a hurricane occurred, and to analyze that you compiled all the tweets. You took the tweets before and after the hurricane. So, now this analysis may go totally wrong, because these tweets are not of the people who experience hurricane, because they might be pretty busy in handling or tackling the situation of the hurricane. These tweets may be of some other people at some other place, so who might not have been impacted at all. So, sometimes this is very dangerous. Now, take the case of sampling also. Let us say there is a company, and that company has a total number of emails, and we take a sample from that. Again, we do resampling for the same data. The the conclusion terms may be different. So, this is actually leading to uncertainty. So this uncertainty because of sampling has a name called as sampling distribution. We also see that gone are the days of data being simple. Now data can be numerical, categorical, binary. Data can be text in the form of emails, tweets, articles. Data can be records in the form of time-stamped JSON files. Data can be geo-based location data. Data can be network data, sensor data. Data can be images. Data can be many more things. Now, these kind of or varied nature of the data may impact the way we do analysis by taking its sample. For example, let us say Facebook users are there. We collect a data set for a week of activity, and I want to draw some conclusions. But these conclusions will be totally wrong because there may be other people who have not logged in at that time, and they may have their observations might have genuinely affected the outcomes. So these kinds of questions are open-ended questions which are research questions for our data science community. Coming to big data, the moment I see the term big data, what comes to my mind? I start describing big data has become big data because of this. Say for example, these are the number of messages on WhatsApp. These are voice calls. These are Facebook user messages. These are photos shared by Facebook users. Netflix user streaming estimate. Instagram stories. So this is indicating huge volumes of data. So that's why big data term is coming. And the moment big data term comes, it is described with the help of 5 characteristics called as variety, volume, velocity, veracity, and value. These are called as the 5 V's. So big data has become big because of this. We started from kilobytes to megabytes, then gigabytes to terabytes, from petabytes to exabytes, from exabytes to zettabyte and yottabyte. So what exactly is happening is with this petabytes and terabytes and exabytes and yottabytes, the data has become large and complicated, and the compilation, the processes becomes difficult, and you need new tools for that. So this big data generation also raised to big data tools which will be handling them. So this is what is big data the moment I refer big data. But as per this author, big data should be a moving target. It should not be like kept at petabytes, or it should not be like kept at terabytes or something like that, because it's a relative term. It goes on increasing. So what big here indicates is the size of the data outstrips the state of the art current computational solutions in terms of memory, storage, complexity, processing speed. So big can mean anything which cannot be fit in one machine, as per the authors. So big data is a cultural phenomenon. It describes how much data is part of our lives, precipitated by accelerated tech advances in technology. Big data can be 4 V's from the 5 V's which you mentioned, as volume, variety, velocity, and volume. Now, when you speak about big data can mean big assumptions. So when we speak about big data, it means collecting and using a lot of data rather than going for samples, accepting messiness in your data, giving up on knowing the causes. So what it indicates ultimately, we are saying that new approach of big data is n equal to all. What is n here? N is the population. So, and I am not taking any sample here, entire thing. But can n equal to all? Say for example, for me there is an election going on, this example, and we are doing polling. For us, what is the meaning of n equal to all? Whosoever came for voting that day. For you, that n equal to all. But there may be thousands of people who might not have come for voting that day because of multiple reasons. They are busy with their job, there are some emergencies, they went to hospital. So whatever conclusions you draw from this n equal to all may be totally wrong. The other aspect is data is not objective. For example, nowadays lot of us say that data speaks. Many of the data scientists say like, let's put everything in and let the data speak for itself. So, but that actually can be, the impact can be like opposite of that. Here the example they have given is, let us say we want to do hiring of good employees, and you are using your say that data, let the data speak for itself, and you compile all the data and you use your model to hire the best employee, and what you identify is men are better than women, because you see that many times women are taking leaves, women are many more things. Uh, their promotions are less, they give more negative feedback of the environment and all that. So this model may select men over women, but that is a bias, right? So it may happen that the company itself is not treating the woman correctly, or the policy is not incorporated in the data collections. There is one more extreme aspect called as n equal to 1. Here n equal to all indicate the entire data, and n equal to 1 indicate only one sample, right? One observation. So in the old days this was not taken into consideration at all, but nowadays with the context of big data, n equal to 1 also can be important. For example, about a single person we can get lot of information, and his every activity, and we may draw some inference from that. This is called as user level modeling. This is called as user level model. So with this we'll stop for today.